have a torque now. This torque creates some stresses in the mechanical components. And the mechanical components that we are dealing here is something that we call it a shaft. Like this one is a shaft. Like this one also is a shaft. And a simple definition is a very long cylinder. We call it a shaft. And shaft is a mechanical component to transfer torque from one point to another point. Usually we use gears like this one, or maybe we use belt, which in the future course, when you learn mechanical design, you're gonna become familiar with designing these components. But now focusing only on the shaft, these shafts come in different forms. They can be a solid shaft. Let me draw something here. First, I need to move myself up there. Okay. So this shaft, if you look at the cross section, and I just draw something bigger. So this is then the cross section. So cross section of the shaft. Sorry, all right. Cross section of the shaft, and it can be a solid shaft like that. It can be a hollow shaft. Let's draw it somewhere around here. Something like that, if I can center it properly. And also it can be a thin wall shaft, more like a pipe sort of shaft. All right, something, let me make it a little bit better. Move it a little bit here. Yeah, let's accept it as it is. Okay, better. So, three types of shaft then: solid shaft, a hollow shaft, and a thin wall shaft. And of course, with each of these shafts, we have, like the shaft has a radius, like this one, the radius, and this one has the outer and inner radius. And just be careful about the thin wall. When we say radius, it is the average radius. It is something between outer and inner thickness. And also we need to have another piece of information, which is the thickness of the wall, right? So this is the thickness, this is the radius, and over here at the top we have radius, and let's show the outer radius with capital R and inner radius with small r, all right? So, but how do we know if the shaft can resist the torque that we are applying? And how do we know that if it is strong enough? If you recall, we introduced something in previous chapter, which we call it moment of inertia. For example, for a solid shaft, we know about, let's say, this x-axis and about this y-axis. If I call, let's say, this x, and this one I call it y, we introduce something which we show it by I, and here, for example, Ix and Iy, they are equal, and for this shaft is pi over 4 R4, right? We call it moment of inertia, and we said it is resistance to bending. Resist to bending. And we learned that the bigger this number is, it means the stronger a part is when we try to bend it. Now, when it comes to twisting, we introduce something else, which we call it I about Z. And Z axis here is an axis which come out of your screen or come out of the plane, which is we cannot show it here because we are showing it in 2D. So I, Z, and mathematically we can prove that IZ is equal IX plus IY, which briefly I explained in module 4. And I talked about it a little bit in module 4. This IZ is the resistance to twisting, resistance to twisting. Meaning that the bigger this number is, the more the powerful or the stronger a shaft is to resist, to twist, basically. And in the example that we have, because Ix and Iy are equal, it becomes pi over 2 R4. And usually, because here we talk about like mostly in a 2D area sort of problems, we have X and Y. This IZ, people show it by J. So that's very common to basically this IZ, show it by the letter J. And it is called polar moment of inertia. Let me write it down here. It is called polar moment of inertia. All right. So similarly for a hollow shaft, this J for this one becomes pi over 2 R4 minus R4, like the big circle minus the smaller circle. For basically for a thin wall shaft, the outer radius, let me show it by RO, is R plus half of T. Don't forget, this R always is the average. So it's not the outer radius, it's not the inner radius. So if in a problem you are given the outer radius, in order to find this R, you need to subtract it by half of the thickness. And the inner radius will be R minus half of T, right? Now it becomes very similar to the previous one. J then becomes pi over 2 RO4 minus RI4. If I substitute this number and simplify it, it becomes something like this, 2 pi R3T. And it's again very common to use this formula for thin wall. So J 2 pi, so this is not R, this is R power 3T. All right, so these three formula is important to remember. And please do not confuse them with moment of inertia about X and Y, right? That one has 4, pi over 4, right? Now we add it, it becomes pi over 2. Okay, so that's the first one for a solid shaft, the second one for a hollow shaft, and the last one, 2 pi R3, R power 3, T thickness. And don't forget this R is the average radius, all right? So to summarize, for each shaft, we look at the cross section and then we calculate a number which we call it polar moment of inertia. The bigger this number is, it means the stronger a shaft in terms of twisting and resistance to torsion, basically. All right. Any questions so far? Are we good? Okay. Now, let's get to the main topic. This is all an introduction. Our goal here is to calculate stress coming from a torsional load. But first, we need to know what type of a stress we create in a shaft. We know for a shaft, if I try to extend it or compress it, the type of stress is a normal stress, right? And again, remember we said in the past, we have two types of stresses. We have normal stresses, like tension and compression, and another type was shearing stress, right? When two things try to slide on top of each other. Our first task is to figure out when we twist the shaft, what is the type of stress creating a shaft. To understand that, imagine that a shaft is made out of lots of discs being glued together, like the one that we showed here in picture A, all right? Lots of discs, we put them together next to each other and glue them together. Now, if I try to twist this shaft, all these discs try to basically slide on top of each other. Now, when I'm saying the word slide, it immediately implies that the type of stress that I'm creating is going to be shearing stress. So let me write. The type of stress is going to be shearing stress. All right, so that's our first task, and it is important to understand it. If like the same things that we have here, lots of discs, we put them together. By disc, let's imagine that you have lots of, let's say, loonies, a coin, and put together these coins, let's say 100 coins of $1, and you put them together, you glue them together. Now you try to twist this long shaft, basically. And basically this disc or these coins try to slide on top of each other. So it's going to be shearing stress, all right? So that's our first task. And shearing stress, you remember we usually show it by letter tau. The normal stress by sigma, shearing stress by tau. And also the formation. Is the length of this shaft is going to become longer or shorter, like when we apply an axial load? The answer is no. It's going to twist, right? Which is sort of intuitive. Let's say if I look at the cross section of this shaft, and if I try to, let's say, draw a line, let's say if I try to draw a line, maybe a horizontal line on this shaft, after we twist this shaft, this horizontal line is going to become something like maybe this new line. So then, which also in this image B, you can sort of see it, right? So it's going to create an angle here. So this is, again, don't forget, this is the cross section. So the deformation then, so this first one then was the stress type. And then second thing, the formation is going to be angle of twist or twisting angle. Twisting angle, which we usually show it by letter phi, or some people pronounce it phi. Both are correct. I believe phi is the correct one. So tau and phi, all right? And in this module, simply our task is to find tau, the shearing stress, or not, because it comes from torsion, the torsional stress, and phi, the angle of twist, all right? It is important to understand where this phi and tau comes from and why it is shearing stress. So if you have a question so far, please ask before we get to the formula and formulating these things. Okay, I assume you are good because it is silent. All right. Now let's formulate everything here that we want to know. Okay, our objective here is to find a stress and also angle of twist. Stress, we show it by tau, and tau has a simple formula, T, R, J. An angle of twist, it has a very, very simple formula. Phi is T, L, G, J. All right? It's very similar to that FLAE, right? Remember that delta that we learned before? So instead of a force, we have a torque here, length the same. Instead of area, we have now J, polar moment of inertia, and instead of E, we have G, which if you recall, this G, we call it shearing module of elasticity. Shearing modulus of elasticity, which for most of material, this G, you can find it in tables, or if you have E and nu Poisson ratio, if you recall, G had this nice formula of E1 plus nu, right? So it's important also to know this formula. Let me get rid of that part. And again, don't forget this phi, the unit is going to be in radian. Okay, it's not going to be in degree, it's going to be in radian. So, sorry about this background noise. Okay, now gone. Good. All right, so the first formula for stress, and then the second formula for twisting angle. Things that we need to know. First is unit. Always we follow the unit similar to the previous modules. If we keep things in millimeters, then the stress is in megapascal and so on. And something that you also need to know is this R in the first formula. Here, R is the radius where we want to calculate stresses, which usually we calculate the stress for like outer diameters. Let's say if it is the cross section, So if for some reason somebody is interested to find stresses in the middle of a cross section, which is very, very rare, then that person puts this radius R here, like R here. But like 100% of the time, we are interested on stress in outer layer, which is the maximum stress, which you can guess why, right? The bigger this R, the bigger this stress is. But if you have a hollow shaft and you want to find out the stress inside the shaft, then you put the radius for inside the shaft, right? So this R is always the radius. So two very, very simple formula, and that's all we need to know about this chapter or this module. It's a very short module, and this is all basically the material for this module. Now, let's see if you have question. If not, then I solved some problem and you realize that how easy it is.
Sorry, I have a quick question. In the bottom one, the bottom equation, what's the unit being added to the one there? Did I just miss that part?
So okay, the formula for G, right? Do you remember nu, the unit for nu?
Yeah, sorry, that's what I thought it was, but I was kind of writing down my notes when you were speaking of it, so I didn't know if that was new or if I just couldn't see what it was.
Okay, sorry for my handwriting. We should blame the basketball that I played yesterday. I told you at the beginning, right? I played a lot of basketball. My handwriting is going to be worse. My hand is sore now. So yeah, nu is the Poisson ratio, and Poisson doesn't have a unit. That's why these G and E have the same unit. All right?
Okay. Thank you very much.
All right. So if there is no question, then let's solve a couple of problems and see how we can put together this formula. All right? And I just emphasize here, these are, if let's say somebody wants to know stress in the middle of a shaft, like inside the shaft, which is rare, and then we use that radius. But if we want to know the maximum stress, then we put the radius in outside, basically outside of the shaft. All right, read this example first and try to understand it, and then we solve it together. Okay, seems to be an easy problem, right? We have a shaft, and it is a hollow shaft. We have the outer and inner diameter or radius, and we apply a torque 4 kilonewton meters, and we have also G. So the question asks simply for tau and phi, angle of twist, all right? So let's see the information that we have. So first of all, T, it's important to decide for a unit. So if you have G in gigapascal, usually I change it to megapascal because it's an easier unit to work with. So it is 90,000 megapascal. Then it means everything has to be in Newton and millimeter. So then T is going to be 4 multiplied 10 to the power of 6 Newton millimeters, right? It is in kilonewton and also it is in meters, so we convert it to Newton meters. And then the next step is J, polar moment of inertia for hollow shaft, pi over 2 R4 minus R4, which for us here is pi over 2 30 minus 20. If you saw somewhere like a formula like that, pi over 32, it is because they put the diameter here. Don't confuse them there, right? So it is D4. Instead of radius, you put diameters, right? Now, if you look, these two formula are exactly the same because D is 2R, right? So we have J, we have T, and what about the length? Length of this is 2000 millimeter. So we want to find out the stress, like tau max is going to be T multiplied by radius, which is outer radius 30 divided by J. We have all the things that we want, and it gives us the number in megapascal. If, let's say, somebody wants a stress inside the shaft, this question basically doesn't ask us, but if for some reason there is a crack inside this hollow shaft and we want to know what is the stress inside this shaft, then it's going to be a stress the same T, but the radius is going to be 20 divided by J, all right? And angle of twist, phi, formula is TLGJ, which basically we have everything that we need. We just substitute this number. T is 4 10 to the power of 6. L is 2000. G is 90,000. And J, we just found J over there, pi over 2. T power of 30 and power of 4 and 20 power of 4. All right? And the number we get here is going to be in radian, which you know how to convert radian to degree, all right? If a question asks for degree. So as simple as you can see, is there any question for this part?
Is torsion always going to be positive, like as terms of sign?
So, okay, a term of sign, so good question. It depends how we define it. If we want to be accurate, right? So if you we look at this shaft from one end, which usually we do, like if this is my eye looking at this shaft, all right? If you look at this T is going to be clockwise, right? So if we want to be accurate, if this T is negative, then it means the twisting also is going to be negative and it's going to be clockwise, right? So Mohammed is asking, what is the sign of this phi? We don't need to worry about the sign, but if you want to be accurate, if we put the sign for T, it means it's negative here. Remember, always for sign, we look from one end of the shaft, and because this T is clockwise, so we put a negative here, we get a negative number, and negative always for us when it comes to rotation or twisting, it means clockwise, right? Or we just simply, we need to say that twisting for this one is going to be clockwise. Clockwise, right? All right, any other question? Are we good? Okay, let me write it down here so later you know. It is clockwise. Now let's solve an example a little bit harder. All right, I'll let you guys to read this example first. I do the same. So it seems we have a shaft, but this shaft, the diameter changed somewhere at point B. And basically, we want to know the stresses in the portion of AB, which has a bigger diameter, and BC, which has a smaller diameter, right? So, and also it says that all the shaft made out of aluminum, we have G, that's good, but we apply basically two torques. One is at point B, which is 800 counterclockwise. So at point B, if I draw it, it's going to be, let's say, something like this. It is TB, which is equal to 800 Newton meters, right? And at point C, which is clockwise. So this is TC, 1,200 Newton meters. And again, don't forget, always we look from one end of the free end of the shaft. Like here, I stand over here. Imagine this is my eyes. Let's say this is the eye. Accept it, eyebrow, and I look at that. So TC is clockwise. The question says clockwise, and TB is counterclockwise, 800 Newton meters, right? So, and we want to find out the stresses in AB and also in BC, and also we want to know, like when we look at this shaft, how much this point C is twisting, basically. That's the question. So, like always, we try to find out the reaction at the support. If I apply this TC 1,200 like that, and TB, so this support A has to also show some reaction, right? And because again, we are in a static and everything has to be in equilibrium, then we can guess, let me draw it bigger, that this TA, so and this is a reaction, has to be how much? Has to cancel these two, right? It has to be 400 Newton meters. And the direction, we can guess it has to be clockwise. See, we have 1,200, or no, I'm wrong, right? It has to be in the opposite. So let me correct this one. It has to be in this direction. Let's check it again and make sure that we are correct. So we have 1,200 going clockwise, and then we have 800, which cancel that one, right? So we need another 400 at A. Now everything is in balance, all right? Does that make sense or no? Any question for this part? Hope everybody agrees that we need a TA, a reaction of 400 Newton meter here. So that's then the first step, the reaction. Also, I suggest that similar to previous chapter, because we don't want to get confused, why not we just draw a diagram for torsional load. So like always, we call this one X, and this time we call it T, because we want to know how T is changing. So this T, we follow the same rules that we learned before. At the beginning, at point A, I have 400, and it is counterclockwise, so it is positive. So I jump up 400. Then everything is constant until point B. Then I have another jump of 800. And maybe if I draw everything's lower, let me move them down there. So I have more room. Okay, better. All right, so let's go back. And what else? So from point B to C, everything is the same. And then at C, we have 1,200 clockwise, which is negative, right? Do you remember always we counterclockwise, we consider positive, counterclockwise positive, and clockwise, we consider it negative, right? And similar to axial load or bending or shearing diagram that we draw, the same concept. We break down these two different areas. Like this one, we say from the beginning, from point A, this is from point A, and this is B, and this is the end of this, basically, beam or shaft, sorry. Okay, so what do we have here? We have 400, and then we have here a jump of 800, so it means we get to 1,200 here. And then at the end, we return back to 0, which means everything is correct. So this diagram helps us to basically understand the torque at each section. So now we know that T from A to B is 400 Newton meters, and T from B to C is 1,200 Newton meters, right? So you may say, well, I don't need this diagram because it's obvious. If I look at C, I have 1,200, and it's obvious that this portion of the shaft from C to B is under these 1,200. And also when I get to B, from B to A, I have like 800, but also at the beginning I had 1,200, so I subtract them, and I know that from A to B is 400. But for more complex problem, it's better to draw this diagram because it helps us to not to get confused, because I've seen again a situation when students, the T from A to B, they write down 800, right? While this is not 800. From A to B, the internal torque is 400 because at the beginning we had 1,200, right? So this is the first and most important part of figuring out the internal torque for a shaft which has several regions. And again, if you have questions, please ask now, because the rest of it is just substituting some numbers. Is there any question, or is it clear? And always I suggest draw this diagram. And this diagram is very, very simple, right? At any point, you break it down to region, like from A to B and then from B to C, whenever there is a change. And at any point, you just follow, when you like this rule, you have plus 400, a jump of 400, then nothing going on, a constant line. And then here you have a jump of 800, right? like this jump is 800. So it gets you to 1,200, then nothing going on. And then at point C, you have a jump of 1,200, which you return back to 0. It means your solution is correct and everything so far is good, because you have to return back to 0 because it is static and everything has to be balanced. In other words, sum of all the torque has to be 0. So let's continue with the rest. The rest is just substituting some numbers. If you want tau, the stress from A to B, you need TAB, radius of AB, which you know it is 20 millimeter, and J from A to B. All right. If you want the stress in portion of BC, so you need the torque from B to C, its radius, which is 10 millimeters, and then J for this section BC, right? Which this J, A to B and A to C is easy. It's a solid shaft. We know the formula. I write it down above here. Pi over 2, radius power 4, and J from B to C is pi over 2, 10 power of 4, right? So we have everything. And don't forget these TA and B, we need to basically use a correct unit, Newton millimeters. And this one the same, right? The rest is just substituting these numbers. And then lastly is twisting, how much this thing is twisting. So because we have section A, B, and BC, I need to find out the twisting that happens from A to B, and also the twisting that happens from B to C, how much this portion AB of the shaft is twisting, how much this portion BC is twisting, all right? So from A to B, we have again the formula TAB. The length between A to B is 1,500 millimeter. And G, we have G, and we have J, AB. And similarly here, TBC, its length is 1,000 millimeter. And G, J, BC. And don't forget this G, it is in gigapascal here, which converted to megapascal. All right. So we found the stress in AB, we found the stress in BC. And by the way, if we follow what Mohammed suggests for earlier for the sign, then we should put this plus here because the T they are positive, right? So this is phi AB, this is phi BC. The angle of twist for the portion of AB and BC. The question wants the total angle of twist at point C, right? Phi total, then it's going to be phi AB plus phi BC. All right, so this is how then we solve a more complicated problem like this one. And now try to check my notes and see if you have any question. So that's the first part, and this is the second part.
I have a question. So is it for Mech 260, are we always going to be looking at shafts or cylindrical shapes? Or we're going to also look at beams later?
Yep. So Mohammed is asking, in Mech 260, always we are going to look at the shaft. By shaft means a circular cross section. The answer is yes. So although you in Mech 360 you learn basically how to calculate the stresses when the cross section is like a square cross section, or maybe like a different shape, like elliptical shape. But again, because they are not in practice, nobody builds a shaft which is like a square shape. It's just some theory that you learn in 360. But in terms of practice, again, 100% of time you're dealing with circular shaft like this one. So yes, in Mech 260, it always is going to be circular shaft, and you don't need to study stresses when the shaft has a different shape, like a square shape. In some teachers in Mech 360 teach it, I do, but again, I emphasize that it doesn't have any application. For example, have anybody seen any shaft, rotating shaft, which is like has the cross section is a square or rectangular shape? I doubt it. All right, so if there is no question, then let's move to the last example. So this is basically the most complex example or problem that you're going to see in this module. And if you understand this one, it means you are good to go for the rest. So first read this one and see, try to figure out what it is. All right. So it seems that we have a shaft made out of two materials. One portion is aluminum and another portion is brass. Right? From A to B is aluminum, and then from B to D is brass. So that's about the material. Also, if you notice, from C to D, the shaft is hollow. So the brass portion from B to C is solid, then from C to D is hollow, right? We apply two loads, TA and TB at two parts. And again, this shaft, it may be a shaft using a gearbox. And this point A and B, they are two gears, basically, create this torque. So our job is finding the stress at each portion and also finding the twist at point A, all right? So first step, like always, we break down this basically shaft to different regions. So if I start from the beginning, point A, then at point B, the material is changing. So anytime something is changing, material, geometry, or a new load, it means a new region. Then at C, the geometry is changing. Material is the same, but the geometry is changing. So that's another region. And then point D, of course, is the end. All right. So I break it down to different regions. And then the next step is try to draw the basically the torque diagram. So let's this time do it fancy. All right. So this is then our X, and this is the T diagram. Okay. We want to draw this diagram. So it's important to find the reaction at the support. So because we are in a static, right, we have 800 going that way, which is counterclockwise. We have 1,600 counterclockwise. If we want these things to be in equilibrium, it means at point D, I have to have a big reaction, which is 2,400 Newton meters, right? To cancel out these two other reactions. And it has to be clockwise. And again, don't forget, always we look from the free end of the shaft. Like this is our eyes. We put it here, and we look that way, okay? Now let's draw the diagram and see if we can get it right, okay? So let's see what we have. So at the beginning here, right, over here, I have 800 and it is positive. So I move up 800. Then everything is the same. Then I have 1600, which is positive. So another jump of 1600. and then I'll go all the way down there, and then I have 2400, which means I return back to 0. So everything is good then. So remember, this one was 800 and positive, right? We jump over here, 1600, positive again. It is positive, so it is to 400. And then we had to move down 2400 negative, right? Because it is clockwise. So we return back to 0. We start from 0, we return back to 0. Everything is good. Okay. So if you get confused with a 3D graph like that, you can draw it like in a 2D form. I just wanted to be a little fancy. Let's move that one up. No, which means I cannot get it right. Okay, let's accept it. All right. Is it clear now? Again, as I said, this is the most important part. If you get this one right, then the rest is easy. Are we good? Okay. So A, B, C, and D. All right. So it means now that from this graph, I know that TAB is plus 800. TBC is 2400. And TCD is also 2400. And they are Newton meter, and Newton meter. And they are all positive. So that's about the torque. If you got this part right, the rest is just substituting numbers, right? So first, also find J. J from A to B, the cross section is solid, is pi over 2, and the radius is 18. Don't confuse it with diameter, so 36 divided by 2. From B to C is the same as C to D. Oh no, they are not the same. It is hollow, right? So from B to C, the material is the same from B to C to C to D, but J is different. It's pi over 2, 30 radius 4, and then J from C to D is pi over 2 outer radius 30 minus inner radius, which is oh, it must. So the question probably forget to tell us the radius. Oh no, it says 40. So it is 20. So the inside radius here, guys, is diameter is 40 millimeters. It is in the question. So this is J, right? We got T, the torque, and we got also J for each section. Now the rest, let's just substitute the numbers. The stress from A to B is TA to B radius, which is 18 J A to B. Stress in portion of BC is TBC. Its radius, which is 30 divided by JBC. And eventually stress in CD is gonna be TCD. Its radius, 30 divided by JCD, right? Keep in mind this tau CD is the stress in outer side of the shaft. If we want the inside stress, then we put 20 here. But we don't need to, because always we care about the maximum stress, and maximum stress happens outside. So we do the same for phi, phi AB, TAB, the distance from A to B, which is 400, and G, JAB, phi from B to C is going to be TBC. Its length 375 millimeters, and JBC. Remember, for each section you put the length for that section, right? From A to B, the length here is 400 millimeters. From B to C, the length is 375 millimeters. And the last portion is 250 millimeters. And then phi CD is TCD, its length 250, JCD. All right. So we also keep the sign, right? Like this T, they are all positive. So we keep this positive sign here. Not over there, sorry. We don't need for stress. But for phi, we better keep the sign. All right. Now we say phi total is going to be sum of all of them. BC and phi CD. All right. So again, that's sort of the most difficult problem that you're going to see in this module. And as you see, if you follow this step, first, find the reaction at the support. That part is easy. In order to balance these torques, you need something at the support to cancel them. And then the next step is draw these T and X diagram, the torsion diagram. Simply start from the beginning, and whatever you see, if there is a load, then there is a jump, 800 and so on. And then the rest, you have two simple formula, tau, TR divided by J, and phi, TL, G, J, all right? And you just substitute this number. If you got the T correct, the torque or the torsion correct, J is just substituting the formula, and then the rest, you just plugged in the numbers and use your calculator. All you need to do in this module. All right, guys, is there